have two attributes in the left hand side. So what I must have to check, one FD is AC determines D. So I need to check whether this can be replaced either by A determines D or by C determines D. Another check I need to perform, one is given as AB determines D. I need to check whether this can be replaced either by A determines D or by B determines D. So let's check that. One is given A determines C. This is FD given. A determines C. So now I am augmenting A. So AA determines AC. Hence give A determines AC. Now A determines AC and AC determines D. So based on transitivity, I am getting A determines D based on IR3 or transitivity. So one of the individual attribute I have got that A determines D. Similarly, I have got A determines B. So I am augmenting A. So A determines AB. So hence A determines AB. So A determines AB I have got and AB determines D I have got. Hence A determines D again I am getting. So both AC determines D will be replaced by A determines D and AB determines D will be replaced by A determines D. So step 4, step 3 I have 5 dependency and step 4 it will be A determines B, A determines C, this AC determines D will be replaced by A determines D, D determines B and again AB determines D will be replaced by A determines D which is already been included. Now we need to check whether there exists any redundant dependency exists or not. Look, A determines D and D determines B. From these two I can get A determines B based on IR3. So this A determines B is redundant. Hence I will be removing this. So at the end my canonical cover will be A determines C, A determines D, D determines B. Again it has got 3 FD but the given FD has 4. So obviously it is in minimal, and since all the attributes, all the FD has got one attribute in the right hand side, hence it will be in canonical form. So this is the canonical cover. Next, students, relation decomposition. This is a very vital topic. Relation decomposition means I may have a compact relation, but that can have thousands of rows, thousands of columns. So we might have some problem to handling data with that complicated big table. So instead of that, instead of handling smoothly or instead of handling so complexity, we can break down a particular table into number of sub tables as per your choice, or the decomposed relation will also be given. But when you will be decomposing, there might be some problem. Decompose so I can do at any random order. Suppose my table has got 5 attributes and 10 columns. So I can take 2 attributes in one table, 1 attribute in another table, and again 2 attributes in another. I can break it down into 3 tables. So relation decomposition is that let a relation R A1, A2, A3 up to An is subdivided into n number of subrelations R1, R2, R3 up to Rn. Then each of these subrelations will be called a decomposed relation, and this process is called relation decomposition. So from a single relation getting number of subrelation is called relation decomposition. But it might have some problem. You might get some additional information after decomposition and then joining, or you might get some less information. Remember that 2 things. Let a relation R is decomposed into n number of subrelations R1, R2, Rn. This decomposition will be called lossless. Lossless means proper decomposition or exact decomposition. If star of R1, R2, R3 up to Rn will give you the original table. Star denotes natural join. So meaning your decomposition will be proper or perfect or exact if after decomposition then I need to perform the natural join between or among all the subrelations. This natural join should give the exact intact original table. If that is true, then we'll be calling this decomposition is perfect. Else, after performing the natural join of the subrelations, if I am not getting the exact relation, then the decomposition is not a valid decomposition, and on that case it will be called a lossy decomposition. Lossy decomposition means either I'll be getting some extra tuple or extra information which was not there in the original table, or I might have some less information. Both can be. Lossy does not mean only that I am getting less information. No, if I am getting some additional information, then also it is lossy. So first I am giving some example, and when I'll be getting some additional tuple or additional information after performing the natural join of the decomposed subrelation, those additional tuples will be called spurious tuples. So if the question comes, how can the spurious tuple be generated? Your answer should be, if a relation is decomposed wrongly, then after performing the natural join of the decomposed subrelation, the natural join can give some additional tuple which was not there in the original table. Those tuples are called spurious tuple. I am giving the example. Suppose the table, the original table is supply. Say the supply. It has got three attributes: S number, I number, P number as some values. S1, I1, P2, S1, I2, P1, S2, I1, P1, S1, I1, P1. These four values. Now I am decomposing the subrelation as per my choice. One is SI, taking only S and I. So S1, I1, S1, I2, S2, I1. S1, I1 has already been taken, that's why I am not taking anymore. Another one is IP, I number and P number. So I1, P2, I2, P1, I1, P1. This I1, P1 I am not taking. And the third part is S number and P number. So I am taking S1, P2, S1, P1 and S2, P1. S1, P1 I have already taken. So these are the three decomposed subrelation. Next I have to make natural join between among all these three tables. So first I am performing the natural join between SI and IP. This will give SIP, suppose. So SIP equals to natural join of SI and IP. So natural join means I need to fetch the common attribute which is I hash. So first S1 I1, and for matching I1 I have I1 P1 and I1 P2. So S1 I1 P2, one tuple. S1 I1 P1, another tuple. S2 I2 P1, another tuple. S2 I1 P2, another tuple, and S2 I1 P1, another tuple. 5 tuples. Now take this table and the third table SP. I am performing natural join. So this is SIP SP, which is the natural join of SIP and SP. So SIP has got 5 tuples, SP has got 3 tuples. So at the end I'll be getting 1, 2, 3, 4, 5 tuples. So first matching attribute is, this is S hash, I hash, P hash. So matching attribute S hash and P hash. This is the matching attribute. So S1 P2, first S1 P2, I need to check S1 P2 over here. S1 P2, this. So this S1 I1 P2 will be there. S1 I1 P2 will be there. Next S1 P2 matching, no matching. Then S1 P1. Now S1 P1 I have 1 column and 2 column. So S1 P1 I2 and S1 P1 I1 will be there. So S1 I1 P1, S1 I2 P1, these three. And then S2 P1. S2 P1 I have 1 column S1 I1 P2. Sorry, S1 I1 P2. S1. For the first S1 P2, I have S1 P2 and S1 P2. wait. First SI and IP. S1 I1 I1 P2. This is I1 P2. So S1 I1 P2 and again I1 P1. So S1 I1 P1. Okay. Then S1 I2 P1. This one S1 I2 P1. Then S2 I1 P2. S2 I1 P2. S2 I1 P1. Okay. Now S1 P2, S1 P1, S2 P1. So S1 P1, how many matching? S1 P1, S1 P1, 2 matching. Okay. And S1 P2, how many matching? S1 P2, 1 matching. And S2 P1, how many matching? S2 P1, 1 matching. So what will be the natural join? First of all, S1 I1 P2 and S1 P2. So S1 I1 P2. Okay. Then S1 I1 P1. S1 P2, S1 I1 P1, and 1 matching is S1 P1. So S1 I1 P1 will be there. Okay. Then S1 I2 P1. S1 I2 P1. S1 I2 P1. So S1 P1 is matching. So S1 I2 P1 will be there. Now S1 I1 P2. S1 I1 P2, S1 I1 P2, S1 I1 P2, S1 P2. So again S1 I1 P2 will be there, and S2 P1, S2 P1 I1 will be there, S2 P1 I1 will be there. So that is the natural join of SIP and SP. Now if I am comparing with the original table, I have got one tuple S1 I1 P2 which is not present in this relation. So after performing the natural join, I am getting this tuple as extra, which is called spurious tuple.
Explain our confused me.
Now let us take another example. This is a relation. Has got EID, job and PNAME, and I am decomposing simple into 2 tables. One table has got EID and job, so take the distinct EID and job. E1 engineer, E2 architect, E1 engineer I have taken, so E3 engineer, 3 tuples. And another table is job and PNAME. Engineer P1, architect P2, engineer P2 I have taken. So if the decomposition is correct, then natural join of project 1 and project 2 will give the intact table. Suppose this table is project. So I am performing the natural join. So first matching attribute is engineer. I have 1 engineer, 2 engineer, and over here 1 engineer, 2 engineer. So 2 into 2, 4 engineer. There will be 4 engineer. So first E1 engineer followed by engineer P1. So E1 engineer followed by engineer P1. Natural join does not inculcate or does not allow the duplicate column. So that's why only job will be coming only once, not twice. So E1 engineer and matching with engineer P1. So E1 engineer P1 and again E1 engineer P2. Take another one, E2 architect. So E2 architect is matching with P2. So E2 architect P2. Again E1 engineer P2, then again E3 engineer P1, and E3 engineer P2. So again, if I am comparing this table and that table, I am getting one additional tuple E3 engineer P1 which is not present in the original relation. So this additional tuple which is called spurious tuple has been added due to the wrong decomposition. So this decomposition is lossless decomposition, as well as this decomposition is also lossless decomposition. Next, the problem is in the exam when there will be asked to check whether the decomposition is lossless or lossy. It's not possible to give always the tabular value that has got some data value. Basically, no data value will be given, only the original relation will be given and the sub relations will be given along with the FD will be given. So based on that you need to check whether the decomposition is lossless or lossy. So that is the algorithm. For a relation decomposition is lossless or lossy. Again, it's a huge algorithm. I'm not going into the details. You just go through the algorithm. You can understand. Meanwhile, I'm telling you the steps of the algorithm with an example. Let this is the original relation R equals to A, B, C, D, E. 5 attributes. Remember, 5 attributes A, B, C, D, E. And the decomposition of R is R1 and R2. So R has been decomposed into 2 sub-relation R1 and R2. And a set of FD is given based on R. So based on this information only, you need to check whether this decomposition is lossless or lossy. No data values given. So come to the algorithm. First input is universal relation R and the decomposed subrelation of R and a set of FD. So this is R, this is decomposed subrelation R1, R2 and FD. This will be the input. Output, whether it will be this decomposition is lossless or lossy. First step, create an initial matrix S with one row I for each decomposed relation and one column J for each attribute in the original relation. So as simple as that, the meaning of this, the structure of the matrix will be like this. The number of rows of the matrix will be number of subrelation and the number of columns of the matrix will be the number of attribute of the original relation. Again I am repeating. This is the matrix S. The structure of the row and column will be as follows. Number of rows will be number of subrelations. Since 2 subrelations are given, so number of rows will be 2. And since 5 attributes are there in the original relation, so matrix has got 5 columns. So the structure is 2 cross 5. Row is the number of subrelation. Column is the number of attributes of the original relation. And step 2 is that set Sij equals to Bij for all ij. You know what is the meaning of I and j index in matrix. So B11, B12, B13, B14, B15, again B21, B22, B23, B24, B25. This is the random assignment of Bij, B value. 11, 12, 13, 14, 15, 21, 22, 23, 24, 25. This is normal matrix assignment. Now come to step 3. What is been written? Forget about all that. Is written for each row I responding a relation schema, for each column J responding in the attributes, if relation contains attributes, set Sij equals to Aj. So first come to the first row, because for each row I, so I have 2 rows, so for all the rows I need to repeat this step. So for R1, I am coming to R1. For each column J, how many columns? 5 columns J. So for each column J representing the attribute, if the relation contains attributes, set Sij equals to Aj. So first A1, B11. R1 has got how many attributes? A, B and C. So the first column, the second column and the third column belongs to R1. R1 has got A, B, C. So R1 has got the first column and the second column and the third column. That's why for this 3 column, the B value or the Sij value, which was initially set as B value, will be replaced by Aj. How many J? 3 J. First, second and third. So A1, A2, A3. Now D is not there in R1, so that's why D will be B14. E is not there in the R1, that's why B15 will be B15. But since ABC is in R1, so the corresponding value B11, B12, B13 will be changed to A1, A2 and A3. Now come to the R2. R2 has got A, D and E. So R2 has got the first column, the fourth column and the fifth column. That's why this B21 will be replaced by A1 because first column, B24 will be replaced by A4 because fourth column, and B25 will be replaced by A5 because E is the fifth column. So that is the purpose of step 3. Next, a big thing. Forget about all those things. I'm coming to the example. Now come to the FD. I have one dependency, A determines BC. Now what is the rule of functional dependency? When I can say A determines BC, I have some matching value of A and in some tuples, and on those tuples both B value and C value will be matched. Then I can say A determines BC. So first identify whether is there any common A value or not. Yes, I am getting A1, A1. So A values are same in two tuples. R1 and R2 A values are same. Since A determines BC, so obviously both BC value have to be same in both the tuples. That is the rule of functional dependency. Otherwise FD will not hold, because FD will only hold, or FD will not hold if I am getting matching value for the left hand side in some tuples, but on those tuples I am not getting the matching value for the right hand side attribute. So A values are repeated in R1 and R2. Consequently both B value and C value has to be same. Now one of the B value is A2, another B value is B22, one of the A value is A3, another C value is B23. But both B value and C value have to be matched. That's why this B22 will be changed to A2 and B23 will be changed to A3, so that A1 A1 matching, then A2 A2 matching, C A3 A3 matching. Otherwise A determines BC does not hold. So since this dependency hold, the left hand side has got some matching value in some tuples, so the right side has to be same on those tuples. That's why one value was A2, another value is B22, so I am changing B2 to A2, and similarly I am changing B23 to A3. Remember, only the B values can be changed, no A values can be changed. If you have all A values, nothing to change. The change is permissible in two cases: when you have matching value in the